This lecture will be the first from chapter 19, which is our last chapter for the spring term of 2020. And this chapter is on the kinetic theory of gases, which is a thermodynamic idea that all of the properties of gases, their pressure, volume, temperature, are due to atoms in the gas that are moving around at different speeds, hitting the walls of the container, and they're responsible for the properties of the gas. So we're going to investigate some of those properties by using that model of these atoms with kinetic energy and kinetic motion moving around in the gas. So first of all, a definition, and some people may be familiar with this if you've taken chemistry. We're going to define what's called Avogadro's number, Na, which is defined to be 6.02 times 10 to the, sorry about that, 23, positive 23 per mole. So what this means is the number of atoms in 1 mole is equal to 6.02 times 10 to the 23. So it could be molecules. It depends on the substance. So you could have, for example, hydrogen atoms or hydrogen H2 molecules. If you have this number of them, you have 1 mole. We can also talk about the molar mass, which is the mass of 1 mole of whatever substance it is, which is going to be different because each individual molecule in a different substance may have a different mass. But the molar mass, in terms of the number of Avogadro's number and the mass of the individual molecules, is just the mass, right, of 1 molecule times the Avogadro's number of molecules. So we can calculate the number of moles just by taking the number of atoms or molecules in whatever sample you have and divide it by Avogadro's number, which turns out to be the same thing as the mass of the sample divided by the molar mass of that particular substance. And again, I just rewrote it here, right? Mass of the sample divided by the mass of an individual atom or molecule times Avogadro's number. So the first and one of the most common things that we do in the kinetic theory is to model the gas as a collection of individual atoms or molecules that are free of one another. We call this an ideal gas. And so the ideal gas, basically what happens is the molecules do not interact with one another. You imagine they just fly right by. Now this is a good approximation if the density of the gas is low, so the molecules aren't generally really close together. If the molecules get compressed close together, then they start to feel forces against each other, and you don't have an ideal gas anymore. You need to make some modifications. But in describing an ideal gas, we're going to use what's called the ideal gas law. And it's related to the pressure, the volume, and the temperature of the gas, and also the number of moles, N. Now, R is a constant called the ideal gas constant. And this expression really comes from experiments. You can do experiments changing temperature, pressure, volume of the gas, and come up with this relationship. And generally speaking, for, again, low-density gases, this works really well. In other cases, you need to make some modifications. But we often say that if a gas has a certain pressure, volume, or temperature, we have a certain state. That gas is in that particular state described by those 3 variables, whatever the values of pressure, volume, and temperature are. This way, the ideal gas law is written in terms of the number of moles. We could also write it in terms of the number of molecules. We just have to change the constant here. And this is called Boltzmann's constant, or the Boltzmann constant, right? And so here's the value of it. And the capital N is the number of molecules. Just by looking at these 2 equations, we can see that the number of moles times R is equal to the number of molecules times K, Boltzmann's constant. So what we're going to do now is look and use the ideal gas law to maybe answer a question. And so I've talked about the state of an ideal gas. So if you change the pressure, volume, or temperature, you change the state. And so we might have questions similar to this. Let's say we have N moles of an ideal gas, at a certain pressure, 1 atmosphere. Now, 1 atmosphere is a certain amount of pascals, 1.01 times 10 to the 5 pascals. But it's a certain pressure in a volume of half a meter cubed, 0.5 meters cubed, and it's at a temperature of 273 Kelvin. So we've defined the state of the ideal gas by giving these values for pressure, volume, and temperature. Now let's say we want to change the state, and we can do it in many different ways, but let's say we keep the pressure constant and make the gas expand to a volume of 1 meter cubed. So we're going to double the volume, but keep the pressure the same against the walls of the container. What is the temperature at this new volume? Right, so again, you can use a PV diagram to illustrate this process. This is a constant pressure process. So you just have a straight line going from state 1 to state 2. And we can write out our values for the variables, state variables over here. Now, to get the new temperature, this equation, ideal gas law, must be the same for every state. So we must have that P1V1 equals nRT1, and P2V2 equals nRT2. So what I could do to relate the two states is divide these two equations. And since P1 equals P2, when I divide, the pressure actually cancels out. So does the N and the R, right? They do not change in this case. The number of moles we're keeping the same. We're not letting any out of the container. So canceling everything out, I get V1 over V2 equals T1 over T2. And this is a general relationship for volume and temperature when you have an isobaric or constant pressure process. So if you double the volume, you'll see that the temperature actually doubles from this expression, solving for T2. So we get a higher temperature, 546 Kelvin. And this kind of makes sense because if you think about it, you have the gas. If you're going to make it expand and still press against the walls, you're probably going to have to add heat to it to make the molecules go faster, maybe. And we'll talk about that in the next lecture. But generally speaking, from the ideal gas law, we can get relationships between two different states of the gas. So we can have what's called an isovolumetric process, which is where the volume is constant, and then you have P1 over P2 equals T1 over T2. Or you could have a temperature constant process, which is also called an isothermal process, and dividing again with a constant temperature here, right? This whole right-hand side cancels and I just get 1. I get this expression, or rearranging it, get P1V1 equals P2V2. Now, actually, if you've taken a chemistry class, they often talk about these relationships, and they call this maybe Boyle's law, Charles' law. They're different laws, but they all come from the ideal gas law, which is the starting point to derive all of them. So you'll see in a homework for chapter 19 an example of having to use this process to solve one of the problems. Now, one last thing we can do with the ideal gas law is calculate the work. Now, in a constant pressure process, right, the work is pretty easy. It's just the area under the graph, like we learned in the last chapter. What if you had an isothermal process? So we want to get the work done by an ideal gas in an isothermal, maybe expansion. So as the gas expands, it goes from a pressure and a volume, P1V1, and it goes to P2V2. Now it'll turn out the pressure drops, the volume expands. We didn't try to do something else to keep it constant in this case, we just let it expand. And in that process, you'll get an area under this curve. Again, the work is the area under that curve, or the integral PdV. Now using the ideal gas law, right, PV equals nRT, or if I solve for P, it's nRT over V. Temperature is constant in this particular case. You can pull it out, get the nRT in the front, and you have an integral of dV over V from your initial volume to your final V1 to V2. Well, the integral of dV over V is just the natural logarithm, and we get this final expression for the work done by an ideal gas in an isothermal expansion, right? And again, right, the general thing is the work is the area under the curve, so you can get the work done for other processes the same way. This is just one particular example that the book does where you actually have to calculate the integral to get the expression.